Alright everybody, welcome back to Math 330. We are going to find solutions to non-homogeneous differential equations with variation of parameters. This covers Chapter 3, Section 5, Part 2. So let's get started. So, why do we need another solution to help us solve non-homogeneous differential equations? Well, our undetermined coefficient method works well if this function f of x is a form of a polynomial, or is a form of an exponential function, or is a form of sines and cosines, or any combination of these. And then when you take its derivative, what you do is you get functions that are linearly dependent on f of x. So the problem comes in is if we have a function f of x where our derivatives are not linearly dependent, say tangent x. If you take a derivative of tangent x, then what you get is a function that's linearly independent of tangent x. And so our methods of undetermined coefficients fails to find a solution to these problems. So we have to come up with a new solution and call this solution variation of parameters. So when can we use this? Okay, we can use this solution if we can find the complementary solution, or the solution to the solution to the homogeneous differential equation, and the integrals that come out of the solution method are solvable. So here's what I mean by all this. So let's say we have the complementary solution right here for our nth order derivative, and what we're going to do is guess our particular solution by taking some function u1 and multiply it times y1, some function u2 and multiply it times y2, so on and so forth. So we're going to make this conjecture that we have a function multiplied times one of our solutions from the homogeneous equation, and that is a solution to a particular, that will be our solution to the non-homogeneous equation. So how are we going to do this? Well, let's say we have a second order linear differential equation right here with a constant p and a constant q, and we set up the homogeneous one, and when we do that, we're going to get two roots. I'm not going to solve for those exact roots. What I'm going to say is I find one solution x1 and another solution x2, and that satisfies the homogeneous differential equation such that our complementary solution is equal to this. Okay. Now that I have that, I'm going to claim that this is my solution to the particular, or my particular solution to the non-homogeneous differential equation. And I have to figure out what my u1s and u2s are. So the way I'm going to do that is I'm going to plug this solution, which should solve this one, back into the differential equation. So I need my first derivative. And so I got my first derivative here. And what I want to do is group this in a little different way. I've got derivatives of my u functions and then derivatives of my x functions. So the derivatives of my u functions are problems with this solution. So what I'm going to claim is those terms equal 0. So that's going to give me my first equation I have to use to help find my u1s and u2s. Then if I do that, my first derivative turns to this, and I can find my second derivative, which is of this form. So now that I have these two derivatives, what I'm going to do is add them up. Alright. So I have my first derivative of my particular solution. And to get that, remember, I'm setting this part to 0. I got my second derivative right here. So what I'm going to do is I have to add to the second derivative p times my first derivative. So here we go. And then I have to add q times the actual function. My particular solution has to equal f of x. So what I'm going to do is rearrange these into this format. Well, how do I get this? Well, I get these two terms right here from there and there, so I'm going to bring them over here, and then I'm going to find terms that have u1s in them. So there's one, there's the other one, and there's the other one, and I factor out my u1s and I get this. And then terms that just have u2s in them right here, and I can factor out the u2s and I get this. Alright, so now that I have it in this order, this is the homogeneous differential equation, so that has to equal 0. And this is also the homogeneous differential equation, and so that has to equal 0. For this is the solution x2 and it's the solution x1. So this equals 0 and this equals 0, and so I'm left with this. This is going to be my second equation, and this is my first, which will help me figure out what u1 and u2 are. So what I'm going to do is take them out, and now I have two. I know my x1s, I know my x2s. If I know x1, I should be able to take the derivative of x1. And if I know my x2s, I should be able to take my derivative of my x2s. I have two equations with two unknowns, so I should be able to solve them. So here we go. So I'll solve the first one for the derivative of u1 with respect to time. I'll take that and I'll plug it back into the second one. And this should allow me to solve for this derivative. So if I do that, I have that. I divide by it. I get this expression. I don't like this fraction here, so I'm going to multiply by an x1 on the top and the bottom. And I get this expression for the derivative of u2 with respect to time. And now if I know that one, I can plug it back into this expression. And then the x1 here will cancel with the x1 here, and I'll get x2 up there, so I'll get this expression. So I have these two expressions. Now when I want to, so I have a derivative is equal to this function. Well, if you look at these functions, they're all derivatives of time, or they're all functions of time. So what I have is two separable differential equations. So I should be able to solve these differential equations for u1 and u2 and figure out what that is. So I need these two. Right. So I have my differential equations that come from my variation parameter method that allows me to find u1 and u2. So let's show an example for problem 55. So this is problem 55. I need to solve the homogeneous one first. So in order to do that, I have to find its characteristic equation. And there it is. I need to solve for my roots. So if I solve for my roots, I get plus or minus 2i. So the complementary solution should be sine of 2x plus cosine of 2x, where y1 is the sine of 2x and y2 is the cosine of 2x. The derivative of y1 and the derivative of y2. So now I know what my x1s are and my derivatives are and my x2 are. So I can set up my derivatives. So I plug them in. You notice down here I have a sine 2x squared, a cosine 2x squared. I factor out my minus 2, it's sine squared plus cosine squared, which is equal to 1. And the minus sign there cancels with the minus sign here, and I get this expression. So I do the same thing. This is the same as this. So I get the same thing down here. So for my derivative of u2, dx is equal this way. And now I have to find my solutions to these differential equations. Alright, so this is just a function of x. This is just a function of x, so these are separable differential equations. So I can set them up that way and solve them. I need to solve these intervals. I have both of these I have to solve. So let's start solving u1. To do that, I have to apply this trig identity right here. I plug that into my interval. It turns into this. Now I can solve my intervals. And I had to do another trig identity for this one, but I'll let you guys look that up. And this is my u1 right here. Now, if I do this for u2, I do the same thing, another trig identity for sine squared x. Use the same one there. I get this interval. And then a trig identity for this can be represented this way. And then I can just solve my intervals, and this gives me u2. Alright, so now that I know u2 1, I can now go back to find my complementary solutions x, y1 and y2, and then I multiply u1 times y1, u2 times y2, and I get this expression. I can simplify that. So this should be my total solution for my differential equation in problem 55. But I want to simplify this a little bit. Let's see. I've got this factor of x sine of 2x, and then the rest I can arrange this way. You see I got a sine 2x times a sine 2x and a 1/8. I got a cosine 2x and a cosine 2x times 1/8. So when you add those together, they just give me 1/8. This term is the only term with x, so that's this term right here. What's left over here is a cosine 4x times cosine 2x, plus a sine 4x plus a sine 2x. There's a trig identity. This ends up being the cosine of 4x minus 2x, or the cosine of 2x. And so this becomes my solution for my differential equation. Whew! That took some time and some work, but the problem is either you use a trig identity for sine squared x and then use undetermined coefficients, or you can use the variation parameter. So now you have a choice of solving the differential equation. It's, like I say in class, there's pluses and minuses to everything. So you have to get some experience using this to figure out which is the best way. Alright, so make some more simplifications, because I have a 2 cosine 2x here and I have a cosine 2x here. So I'm going to group them together, and this is the simplest form I can have for my solution for my non-homogeneous differential equation. Alright, so let's try another example, this time with problem 56. So let's bring back our formulas that we got from our variation parameter technique, and we're going to be solving this differential equation this time, and we need to find the solution for the homogeneous differential equation, and we find out that our characteristic equation is this, and our solutions are plus or minus 2. So that gives me a complementary solution of this format. So I get my y1 is this, and my y2 is this. My derivatives of y1 and y2 are that. And that allows me to help me figure out what u1 and derivative of u1x and u2x should be. So that simplifies to that expression. And then I can simplify my u2, the derivative of u2 with respect to x expression to this amount. So have to find my integrals. So I have these two separable differential equations, which would give me these two integrals. So I can solve this first one. I'm going to have to use integration by parts to solve this, both of these. So my u is going to be x divided by 4, and my du is going to be e to the minus dx. So my du is 1/4 dx. My v becomes a minus e dx. And we put it into the formula of uv minus the integral of v du. And we get this integral. And so I can solve that quite easily, and it's this. So that's my u1. I can do the same for u2. So for my integral for u2, I get u is x divided by 4. My dv is e to the 3x dx, and my du is 1/4 dx, and my v is 1/3 e to the 3x. And this gives me my, so u2 has to be the integral of uv minus the integral of v du, and that's what I get here, and I can easily solve this integral here now, and I get that expression for it. And so now I know what u1 and u2 are. I know what y1 and y2 are, and I can get my particular solution now. So what I can do is simplify. I'm going to use these powers of exponents because if I multiply them through, I got an e to the 2x and minus x, so that should be an e to the x. So I have this expression. I could probably factor out the e to the x that I want and the 1/4, and then I get this expression over here because I have e to the minus 2x times e to the plus 3, which would be e to the x. So I could, and I can simplify these a little more. I can find common denominators for the x minus x to the 12th and minus x to the 4th. If you do that, you get this expression. Same with these. I get this expression. I bring back my complementary solution, and my full solution turns out to be this. And that's as simple as it can get. That is my solution for problem 56. So I give you two examples right here. We'll do some more examples in class, and I hope you have a better understanding now of how to use variation of parameters, and I'll see you in class.